These are the 4.1 part 1 notes, and we're going to start looking at polynomial functions. 4.1 encompasses a lot of information. We're actually going to spread this out over four separate note sections, but we're just going to start with some of the basics of polynomials, and then we'll move on from there. So what is a polynomial function? A polynomial function is the function in the form of a subscript n times x to the n power plus a to the n minus 1 times x to the n minus 1, blah, blah, blah. Polynomial function is a function whose rule is given by a polynomial in one variable. The degree of a polynomial function is the largest power of x that appears. The zero polynomial function f of x is equal to 0 is not assigned a degree. Any other constant function has a degree of 0. Polynomial functions consist solely of multiplication and addition, and therefore are considered to be some of the simplest functions to evaluate. So we've already been working with polynomials, and you've been working with polynomials since Algebra 1. Linear functions, technically speaking, are considered polynomials. Quadratics are considered polynomials. Cubic functions are considered polynomials. Once we get past that, we don't give out names. We don't really say like quartic functions or pentic functions. We just kind of at that point start calling them polynomials. And we've got a lot of properties. Now this script up here where it says like this is how it's defined, this is a very mathy way of saying it. Basically this is just saying that like you have to have your coefficients and variables in descending order of power. Or degree is probably a more accurate term here. So my coefficients and variables are in a descending order of degree. So let's say that I had something to the fifth power. I would say f of x is equal to 2x to the fifth minus 3x cubed plus 2x squared minus 2. The important thing here is I am descending in order of my powers. So I'm saying like my fifth is followed by my third, is followed by my second, is followed by something where it's a constant, there's no variable there. So if I have a variable in a polynomial function and that variable is being raised to a specific power, I always start with my greatest power and then I descend in order from there. And that's called standard form of a polynomial function. It's just like when we did quadratics, how you have that ax squared plus bx plus c. There's a reason standard form exists in that order. It's because quadratic functions are still polynomial functions, so their standard form is no different. It's just that it's a very specific type of polynomial function which we can gather a lot of different information from. Looking at some polynomial functions here, we want to be able to determine if it's a polynomial function or not, and then state its degree for a, and then assume that all of these have f of x written. So all of these should be f of x. I just didn't put that in the notes. So if I say here f of x is equal to 2 minus 3x to the fourth, this is a polynomial. All I see is multiplication and subtraction. So that checks out. And then it's a fourth degree polynomial because I'm raising it here to the fourth power. So fourth degree. And then technically speaking, I'm not going to make you do this quite yet, but I would have to say technically this polynomial is actually negative 3x to the fourth plus 2. I need to put it in that descending order. That's the standard form here. B is not a polynomial. This is a square root function. This is a radical function. Taking a square root is no longer just multiplication, addition, and subtraction. This is listed as x squared minus 2 over x cubed minus 3, or minus 1. This is what it would look like in your textbook, where I would say f of x is equal to this. This has a variable in the denominator. So this is a rational function. This is like when we had our reciprocal functions, but we call them rational when we start doing some more things here. So this is not a polynomial. F of x is equal to 0. As defined in this previous slide, f of x is equal to 0 is a polynomial. So we say yes, polynomial. However, it has no degree. This is the one specific case. Now let me see if I have this example. Yep, g of x is equal to 8. This is also a polynomial. But this is considered a 0-degree polynomial. So that's where it gets a little bit tricky. If you have f of x is equal to 0, if you just say that you have a constant function where y is always 0, it is technically a polynomial by definition of a polynomial, but we don't give it a degree because it's just the number 0. If you have any other number, if you say that it is equal to just some number, then yes, it still is a polynomial, but we say that's a 0-degree polynomial. Finally here, right now, I can tell you that this is a polynomial. All this is multiplication, subtraction, addition, etc. So yes, polynomial. But we don't know its degree right away. I can't look at this and say that this is a 3rd-degree polynomial because I still have to actually complete my multiplication. So I have to say h of x is equal to negative 2x cubed times x squared minus 2x plus 1. I got that from expanding this. I said x minus 1 times x minus 1. I did my distribution, and then I added my middle terms. Then I have to distribute this, so I end up with h of x is equal to negative 2x to the 5th power plus 4x to the 4th minus 2x cubed. And now I can look at this and say, okay, my highest degree here is the 5th. So this is a 5th-degree polynomial. So that's pretty straightforward. To figure out your degree, you just look at the largest power you have. You don't look at any other powers. You don't add them up. It's just the largest power. It's based off the leading variable. And again, that's why standard form is so good. We know exactly the degree of our polynomial based off the fact that we are looking at the first term. And then we can tell if it's a polynomial just kind of based on, okay, is it just multiplication, addition, and subtraction, or do we have something going on? Do I have a variable in my denominator? Do I have a square root sign, etc.? All right, smooth and continuous functions. This comes more in play in calculus, but you will learn that polynomials are smooth and continuous functions. Smooth functions mean there's no corners or cusps, and continuous means you can draw the graph without lifting your pencil. So here you can see that I can just go ahead and I can barely trace things to save my life, but you can see that I can make the outline of this shape. It's not perfect, but I don't have to lift my pencil. It's smooth, it's nice, it's clear, you don't have any ugly corners, cusps. Now if I look at B, I go through, I kind of make my graph here. I've got a terrible corner, I've got a terrible cusp, and then I get to a gap, and then I have to stop and then pick my finger up and start again. I have to pick my finger up at the hole and then start again. So that's not continuous. I've got two areas here that aren't continuous. It's the gap and the hole. And then I've got those cusps and those corners that make it not a polynomial. I can look at that graph and immediately say, whatever equation this is being given by, it's not a polynomial function. I can guarantee you that. So now we're going to start looking at some even degree polynomials. I really want to qualify that this does not mean it's an even function. So even degree does not equal even function. Even function is something very specific. Even function means that we have something that has y-axis symmetry. Even degree just means that we are talking about a polynomial that has an even degree. So if I have f of x is equal to 2x to the 4th power plus like 3x cubed minus 2x, the fact that we have this 4 and this is a 4th degree, I'm saying that the degree of the polynomial is an even number. And that's all I'm saying by saying it's an even degree. I'm not saying it's an even function or anything like that. I'm just saying I have this. So we've got some properties of just basic even degree polynomials. These are parent functions here. So I've got x squared, I've got x to the 4th, x to the 10th, x to the 10,000th. And we can kind of see what's happening here. That if I have no transformation, so if I just have f of x is equal to some x to an even power. This is all I'm saying. I'm not saying that I've transformed anything. I'm not saying that I've moved anything. I just have f of x is equal to x to the even power. I know that my domain here will be all real numbers, and my range will be from 0 to infinity. You will have an x and y intercept at the point 0, 0, which would also serve as a vertex value. Now, one thing that I do want to start getting used to is I want to start getting used to some language here. So as x approaches negative infinity, so this means as x gets closer and closer to negative infinity. And what I mean by that is this is x approaching negative infinity. As I move more towards the left, my x values are getting to be smaller and smaller numbers, technically speaking, or larger and larger magnitude in the negative direction. Y approaches positive infinity. So as x is going towards negative infinity, y is still going up towards positive infinity. As x approaches positive infinity, so as I have my x values move to the right, as my x values get larger and larger and larger, my y values continue going up. So my y values here also continue going to positive infinity. And we can see that all of these have like a lot of things in common. If I just have f of x is equal to x to an even degree, I know that every single one of these has this table of values. X is negative 1, y is 1, x is 0, y is 0, x is 1, y is 1. I can only do that with those 3 points. Outside of that, everything else is very different, and we can see that here through my 4 functions that I have graphed. The only place where they intersect is at 0, 0, and 1, 1. Everywhere else, when I have x to the 10,000, I'm almost looking at like an immediate U shape because I'm making these numbers grow very, very quickly. X squared is a little bit more, less like truncated U. It doesn't look so blocky. It's more smooth. And we can see that as I go from x squared, x fourth, x to the 10th, my U kind of flattens more and more and more and starts taking on more of that boxy shape. Because when I start multiplying fractions by themselves over and over and over, I start getting really, really small values. So those values get really, really close to 0. But what this is going to allow me to do is just make some basic transformations. And we're going to start expanding on this. You might be asking, what's the purpose of this? Why am I looking at just properties of a function if it's raised to an even power and there's no other transformation? Well, this does give us some good information about what these functions look like. And you'll be surprised at how much, when we start getting to end behavior of functions, a lot of it's still based off just this initial information of the parent function. And we're going to learn about how the degree of the polynomial, how multiplication, how that actually impacts the graph a lot. So this is important stuff to take in, especially when we start looking at this language of x approaching negative infinity, y approaching positive infinity, etc. All right, so properties of an odd degree polynomial. Again, just like with even function, odd degree does not mean that it is an odd function. Yes, it can be. I will say that. An odd degree function could be an odd function as well, but just because it's an odd degree function does not mean that it's an odd function. So here, when I say an odd degree function, I'm saying like if I have f of x is equal to x to the 7th minus 4x to the 4th plus 2x squared. My largest degree here is still a 7th degree, so this is an odd, it's 7th, so it's an odd degree. So let's look at some of the properties I've got going here. Well, first of all, my domain will be all real numbers, and in this case, my range is going to be all real numbers. I've got it going both directions. As x approaches negative infinity, so again, as my x values, as I go towards the left, as I'm looking at my x values getting a larger and larger magnitude in the negative direction, y also approaches negative infinity. My y values are going down in this case, so that's negative infinity. As x approaches positive infinity, so as my x values are moving farther and farther to the right and getting bigger and bigger values, my y values are going up here. They're approaching positive infinity. They all have an x and y intercept at 0, 0. And then I can make the table of values for all of these -1, -1, 0, 0, and 1, 1. I've got these 3 points which are in common. And again, this is just for a parent function. This is just saying I've got f of x is equal to x to some odd degree. I've done no transformations. I don't have anything else along with it. I just have that information here. And again, we see a lot of similar things to the even functions. When I have those really large degree odds, I have almost like right angles occurring at -1 and 1 as my function kind of goes from being on the x-axis to almost being directly equal to like infinity right away. I have a very smooth cubic function shape for just x is equal to x cubed, and then it expands out and gets closer and closer and closer to that box shape. We can even think about the fact that a linear function of just y is equal to x. So if I want to add in, just for fun here, I'll say y is equal to x in my 5th line. That means I would have a point here, I would have a point here, so on and so forth. So I would have this line that goes through all these points, and we can see that slowly we're moving away from having decimal values and we're getting closer and closer to 0 as we increase the degree. Just like happened with odd functions. Again, when you start taking those fractions and multiplying them by themselves over and over and over again, you get really small numbers close to 0. So that's just a cool way to look at this and see that we're looking at something that still goes to the point 0, 0, still goes to the point -1, -1, 1, 1. All of these have the exact same properties. All right, so now graphing transformations, we can graph the basic transformations from -1 to 1 of all these parent functions since we know their behavior. The same transformation rules apply. So if I look here, I've got a parent function of f of x is equal to x to the 5th. Well, I know that my table of values for x to the 5th is going to look like this: -1, -1, 0, 0, 1, 1. So if I shift everything to the left or to the right by 3, I'm adding 3 to all my x values. Well, now my table of values is just 2, -1, 1, 3, 0, and 4, +1. So my function now looks like this. I've got my origin happening here. I've got a point 2, -1, and I've got a point, and I can draw kind of that x to the 5th shape. That's what it's going to look like. It's just that simple. I know that that's the table of values for its parent function, and I can do that simple transformation right there. If I've got f of x is equal to x to the 10th plus 5, I know that since this is an even degree function, its table of values normally would look like -1, 1, 0, 0, 1, 1. And since I'm adding 5 and it's outside the parentheses, it's after the input has occurred, I'm saying that my new table of values would look like this. X is equal to -1, 6, 0, 5, 1, 6. I'm just doing a vertical shift, and I can do it with those points. So, -1, 1, 1, 2, 3, 4, 5, 6. So I've got my point 0, 5, -1, 6, +1, 6, and then I can draw that same shape. And it looks a lot like a parabola. It's going to look a lot like a parabola. That's okay. So all I did was just go through and say to myself, I know exactly what this function looks like. I know its initial table of values. I know these 3 points. I can graph this transformation. Now I can only do it through those 3 points. I don't look at 2 to the 10th power. That's a massive number. I'm not about to graph 2 to the 10th power. That's a massive number. But I can make this transformation just between -1 and 1. And then finally, we've got our transformation for 2x to the 19th power. Again, this is an odd degree polynomial. I know that its table of values looks like every other odd degree polynomial with prior to transformation, where it's -1, -1, 0, 0, 1, 1. And what I'm saying here is that I'm multiplying my y values by 2. So I actually have this table of values. -1, 2, 0, 0, 1, 2. And then I can go through, make my coordinate plane, -1, +1. My first point will occur at -1, -2, then I've got 0, and then here, and then I can draw my same odd function shape. They all have that squiggle shape just like an x cubed does. They get a little bit flatter towards your x-axis between 0, 0 and -1 and 1. However, it still has that same shape for the most part. And then I can graph that function, and that's all I have to do. I just use that same table of values and then just do basic transformations with those parent functions. All right, you guys have a homework assignment tonight. Please reach out with any questions or concerns, and have a great night.